Video on section 2.6. I have to make a little correction to the previous video. In the previous video, I wasn't paying attention, and when I was trying to write absolute values in all of this, I put little feet on them. And so that's the notation I should be using for the floor function. I was not paying attention. I guess this is one downside of video that I can't just go back and erase it like I would on a chalkboard, so I'm just saying all of those should have been absolute values. So my apologies for making that mistake. Hopefully that's not confusing. Let me know if you have any questions. So in this video now, the most important thing that we're going to do is that we're going to use the squeeze theorem in order to show that the limit as theta goes to 0 of sine theta over theta is equal to 1. So back in section 2.2, when we first started to explore what is a limit, and we had the definition of a limit, and we saw how we could examine limits by graphing them or by figuring out values and stuff like that. We saw that we had pretty good evidence for this. So we just plot this out. It was looking something like this, where that's 1 right there. And so we felt pretty good at saying that, yeah, using our graphical and numerical methods, we're pretty sure the answer is 1. Well, now in this section, we're going to show that the answer is exactly 1. And we're going to show that rigorously. And we're going to do that by the squeeze theorem. So the squeeze theorem, recall that we are looking for upper and lower functions that bound our function from above and below, where each one of these we can easily calculate the limit of, and those two limits need to equal. So we're looking for two functions that are going to bound sine theta over theta, and as it turns out, those functions are going to be 1 and cosine theta. And so in order to, so now our work is basically into two parts. So the first part is to justify these inequalities. And I should say these inequalities are valid for theta is between minus pi over 2 and pi over 2. This first inequality is not valid for every single value of theta, but it's just valid for theta between minus pi over 2 and pi over 2 is the only thing that we need. And as I said, that's the only thing that we need. If we bring back the slide for the squeeze theorem, we can see here that assume we have L of x is less than or equal to f of x is less than or equal to u of x for some open interval around x is equal to c. So minus pi over 2 to pi over 2, that gives us a nice open interval around theta is equal to 0. And so our work is in two parts. Number one, we want to show this pair of inequalities, and then we'll apply the squeeze theorem to get the desired conclusion. So in order to come up with this set of inequalities, I'm going to draw the following set of pictures. There are 3 pictures to draw, and so each one of them is going to start off with me drawing a unit circle. These are all unit circles. And at each one of these 3 pictures, I'm going to shade in a different area. So I'm going to draw on each circle, I'm going to draw the same point, where this point has coordinates cosine theta and sine theta, cosine theta, sine theta, cosine theta, sine theta. And so now let me shade in 3 different sectors. And I guess it's worth me saying that each one of these points right here is 1, 0. So the first sector I'm going to do is I'm going to make a triangle. It's going to start at the origin, go up to cosine theta, sine theta. It's going to come down to 1, 0. And so that is let me call this area 1. The second one is going to draw the same line from the origin to cosine theta, sine theta, but instead of drawing a line from here to 1, 0, I'm going to shade in the entire pie slice. And then the third example, the third one I'm going to do, I'm going to draw a line segment that's going to go, again, start from the origin, go through cosine theta, sine theta. It's going to go all the way out, and I'm going to draw a straight line up from 1, 0, and I'm going to draw until those two lines intersect. And so the third area is, so I have A1, A2, and A3. And so now our goal is going to be to compute those three areas in terms of theta. So first thing to observe, this point, cosine theta, sine theta, is at the exact same point. We're assuming that we have the same value of theta in all three of these pictures. So obvious statement number one is that these three areas, A1, A2, and A3, A1 is clearly smaller than A2. Why? Because of that little sliver right in there is missing, and this one is present in that one. So this area over here is strictly bigger than this one, because the only difference is that we're missing that low slice there. And then correspondingly over here, A3 is clearly bigger than A2. Why? Well, A3 contains, these two regions are exactly the same, and then A3 contains more stuff up here. So first observation to make is A1 is less than or equal to A2, which is less than or equal to A3. Okay, so now that we have these three expressions here that are related by this pair of inequalities. Hint, hint, wink, wink, nudge, nudge. Somehow that's going to correspond to these three things up here. We'll get to that. Let's go ahead and figure out what are the areas of these three regions. So this first triangle, well, it's a triangle. So we know how to figure out areas of triangles. It's the area of a triangle is base times height, where the base there is 1. We're going from 0, 0 to 1, 0. So that's base 1. And its height is exactly the y-coordinate there, which is sine theta. So the area of this first region is 1/2 times base times height. Okay, now let's look at the second region. The second region is just a entire pie slice, an entire pizza slice. And so the area of a sector, so this is a high school geometry fact, is this is just 1/2 times the value of theta. Quick confirmation of that. If theta is 2 pi, then we're looking at the entire unit circle here. We get 1/2 times 2 pi, which is pi, and the area of a circle of radius 1 is pi times 1 squared, which is pi, so that checks out. So the area of this sector is just 1/2 times theta. So what do we have? We have this inequality. Now we need to think about the third expression here. So once again, this is a triangle where we have to figure out what is the base and what is the height. So once again, our base is 1. And so our height here actually ends up being tangent of theta. You can see that just by thinking about what's going on here, cosine theta, sine theta, some similar triangles and stuff like that. Actually, you know what? Let's omit that for the time being, and just go ahead and say that the area here is 1/2 times 1 times tangent theta. So to summarize what we have 1/2 times sine theta is less than or equal to 1/2 theta is less than or equal to 1/2 tangent theta. If we clear out, there's a 1/2 every place, so we could just clear that out and say it's just sine theta is less than or equal to theta is less than or equal to tangent theta. So looking at this inequality, rearranging this gives sine theta over theta is less than or equal to 1. And rearranging this inequality, so we have theta is less than or equal to tangent theta is sine theta over cosine theta. And rearranging this one, moving the cosine up, moving the theta down, gives cosine theta is less than or equal to sine theta over theta. And so we can combine these two together to get cosine theta is less than or equal to sine theta over theta is less than or equal to 1, which is exactly what we wanted to have here. So now our final step to put all the pieces together. So we have this pair of inequalities, and so so this is valid for theta, for an interval of theta around theta is equal to 0. So we note that to finish this off, all we have to say is the limit as theta goes to 0 of cosine theta. So we can do this one by continuity. We know cosine is continuous. So this is just cosine 0, which is 1. The limit as theta goes to 0 of 1 is just 1. And so, hooray, we have trapped sine theta over theta between two functions, both of which have limit 1 as theta goes to 0. And so we say that the limit as theta goes to 0 of sine theta over theta is equal to 1. If you want to see the picture for all this, perhaps I could have done the picture earlier, but I'll go ahead and do the picture now. So here is 1. And so our upper function is just the constant function 1. The lower function is cosine theta. And so somehow sine theta over theta is trapped between those two. They get squeezed together. These both go to 1, so we can squeeze sine theta over theta to also be 1 as theta gets close to 0.